Good afternoon. This is Julie Bloomquist. I'm part of the Database Administration Virtual Chapter Moderators Group, part of PASS. Today we're going to have a lecture on in-memory indexes, not the same cup of tea as disk-based. And the presenter will be Mike Bird. We wanted to thank our sponsor, Quest, for sponsoring our virtual chapter. We have discounts available. So if you are registering for the PASS 2018 Summit, we have two different codes. One will give you access to stream the PASS Summit 2017 sessions, and the other will give you $150 US discount. You cannot combine the discounts, and as a virtual chapter, we will get monies when people use our codes that we can then use for raffle items. So please keep this in mind if you're registering for Summit. PASS is looking to connect with new sponsors, so if you have suggestions, you can send those in. We are one of the virtual chapters. There are quite a few virtual chapters. All you would need to do is take your PASS login and associate it with either a virtual chapter or a physical chapter, and you get emails about upcoming meetings. SQL Saturdays are one-day mini conferences. Some of the SQL Saturdays are now having pre-conference classes with them. These are the upcoming SQL Saturdays around the world. And again, here's information about how you can join a local chapter. So again, you just would associate your PASS account with a local physical chapter, and it's again in-person learning and networking. And if you don't have a local chapter in your area, PASS is able to assist you with getting one started up. PASS also has opportunities for volunteering. Just go to the new My Volunteering section of your PASS profile, and they're always looking for individuals who you could help with virtual chapters, you could help with conference. There's a lot of different positions available. And then there's also the Outstanding Volunteer Award. So every month it's intended to honor someone who has really dedicated themselves to SQL Server and to PASS. So today, like I said, it's in-memory indexes. Mike Bird. Mike's a former rocket scientist and USAF fighter pilot, and he's now a SQL Server geek. Past opportunities include freelance technical writer for PC Magazine, senior software manager for a government-sponsored munitions effectiveness committee, and an IT director for a Texas Windstorm Insurance Association, and he did that for 9 years. Currently, he's a senior database consultant for several companies. It's an ideal job. It's SPROC and query performance tuning or T-SQL instructions, specialties in SQL Server performance tuning, both the database OLTP and OLAP architectures, and troubleshooting. And he also teaches T-SQL basic through advanced, and he's also a speaker at SQL Saturdays. So thanks, Mike, for joining us. I'm going to switch the presenter over to you.
Okay.
Oh, great. Now I have to, here you go, Mike Bird.
Okay, you should see my cover slide now. Good morning, everybody, or afternoon or evening, wherever you are in the world. Today we're going to talk about SQL Server in-memory indexes, and they are they're same, but they're also different than disk-based indexes. So we'll try to point out the differences as we go along. I hope you understand me. I speak Texan. I live about an hour west of Austin, Texas, and every morning I wake up to and have breakfast with that picture you see there looking out over Lake LBJ. It's a hard life, but somebody has to pay the property taxes. There's my contact information. I put up a zip file to Julie and to Sharon that they can, so you can download both the PowerPoint presentation and the 2 demo scripts that we'll go through today. Anyway, so you'll have the contact information if you download that zip file. So as Julie said, I really was a rocket scientist. I have a master's in rocket propulsion from Purdue, as well as I worked at the Air Force Rocket Propulsion Lab for 3 years. I flew fighters in Air Force, F4 and F5, did freelance writing for PC Magazine, and most importantly, though, is who I am, and what I have always strived for is performance, whether it's in a rocket engine or racing sports cars or flying fighter planes, or now just being a geek and SQL server. And I always just love to solve the performance issues wherever they might pop up. This presentation today is actually part 2 of a sequence of presentations I've done in the past. The first one was on in-memory tables. You can find it at that SQL Saturday 597 and download the presentation there. If you want to see it written, though, you can, let me switch screens here. You could go to logicalread.com, which is SolarWinds, and if you do a search on Bird, and you can see right here is part 1. It says part 1 or part 2, but really this is a 2-part series of blogs I did on the first session I did on in-memory tables. I don't have a blog yet on in-memory indexes, but today we're going to look at 3 types of index types: a hash index, a range index, and column store. Lots of demos, and then we'll look at what we talk about, what we've found as we go through. Let me switch back. And all the demos today will be with the VentureWorks 2017 Big. Big is just mean that I ran a script by Jonathan from SQL Skills to increase the table size of sales order detail and sales order header. We'll talk about that in a second also. Just as a side note, a standard edition of 2016 Service Pack 1 2017 now has index compression. Woohoo, I love index compression, especially row compression. RTM CU4 is now available for 2017, and Management Studio version 17.6 is available, and that's what I'm running with today. So let's regress back, just go over a summary of what happened in part 1. Microsoft, and I'm not a I don't work for Microsoft, but they did take a different technical approach for in-memory tables, mainly because RAM's getting cheaper. The processors are pretty well leveled off in performance, and most of the relational databases are based on designs back in the 80s. So they took an approach of, well, what can we do to reduce CPU cycles? And they did it by two methods. One, making in-memory tables into a C# data structure and creating them as a DLL. And the same thing for in-memory stored procedures as C# DLLs. I hope these numbers show up, but their design goal for in-memory tables was a factor of 10. Well, for bulk inserts, they achieved, as you can see where my cursor pointer is, about 2.5, a little bit over 2.5 for bulk inserts on improvements. With an insert with a select, you can see it runs up to about 4. But look at the deletes. I mean, they well exceeded their 30-fold improvement in deletes. Updates, a significant performance increase there. The second column here is in-memory table with a column store index. So if you're updating a single column, you still have to rebuild the column store index, because in in-memory tables, the column store index is the entire table. Excuse me, got a frog in my throat. Got allergies here in Central Texas. Update, we saw factors of 10, again, the reset, or with over a range. One place, though, that was interesting for in-memory tables, and I had a long talk with Bob Ward about it, was that Table scans for in-memory tables are roughly the same, if not just slightly less than a disk-based table. Of course, it depends on the number of physical page reads as opposed to logical page reads. Where column stores start to really show in memory indexes is an increase in improvement is in select statements, and that makes sense because that's what indexes are all about. So you can go through those numbers later if you want to, but the results of part one was they offer a fair amount of performance enhancement, but you have to make sure you have enough RAM to in your server, and you have to do error checking on the sprocs. There's a concurrency issue that could occasionally pop up and require some error checking. But again, that's all discussed in the other one. And consider 2016, 2017 because there's less restrictions. But this presentation today is on how to use indexes. That's what we're going to talk about. In-memory indexes. Be very careful of what you read out there on the internet. There's very little current information from Microsoft or anybody else on in-memory indexes and how to use them. There are many results when you Bing or Google the in-memory indexes, but most of those are out of date or just say the wrong thing. For example, there's several articles that say you can only specify your bucket count for bucket indexes at table creation, which was true for SQL Server 2014, but it's not true for 2016 and 2017. And I give an example of an alter table where you can change the bucket count there. My recommendation is if you're going to use, and we'll see that as we go through, if you're going to use in-memory indexes, and I do recommend using them, that you experiment. So every memory optimized table must have at least one index. If there's schema and data durability, then you have to, that index has to be a primary key. In-memory indexes, you have a maximum of 8 indexes per table. And the index structures are not persisted to disk. They exist only in memory. They're not logged. Index operations are not logged in transaction log. The index structure is created at table creation or when you start SQL Server or you alter the index. The pointer is to an actual row in the C# data structure, not to the primary key, which is kind of nifty. And you'll see some fallout of that in a few seconds. You don't have to worry about fragmentation or fill factor or pages because it's all in the C# data structure. And the best part I like about it is there's no need for covered indexes. The row data is all there because it's pointing back to the actual row in the C# data structure. Nifty, I think, anyway. So as I said earlier, we have 3 index types. We have a hash, range, and column store. Column store came about in 2016, also for 2017. Did not exist for 2014. Hash indexes. Data is indexed through a hash table. It's always a fixed size, and you have to specify the size. No matter what you specify, it's always going to round up to the next larger power of 2, and I'll show you that in a few seconds in the demo. Each bucket is 8 bytes, and even though you may have roughly the same number of buckets as the number of distinct rows, you're still going to have empty buckets. They're very efficient for point lookups. Well, that's what everybody advertises. That's not true. It's very efficient for point lookups if you're on a unique column. If the column is not unique, then it starts storing the same values in the buckets and uses a linked list to get down to navigate through that. And that's very poor from a performance point of view. If you're using more than one column for a hash index, you need to specify all the columns in your lookup in your select statement or your where clause. If not, it won't use the index. And like I said just a second ago, performance drops when many duplicate values are in a bucket. Does not perform well for a range of values, like a date range, for example. And it's preferable over a range index when the where clause is an exact equality on all the index key columns. And I'll show you that in a demo where you don't have all the key columns and where you do have all the key columns. There's an excellent article on determining bucket count at that link there. And if you download this file and then you can click on this link and it takes you right there. Range indexes. It came in 2014 Service Pack 2. And you can think of them almost just literally as a non-clustered index for a disk-based table. They support very well retrieving ranges of values. They support result order columns in the index definition. They're very good when you have greater than, less than, or between operators. And again, as I said earlier, there's no need for covered indexes because all the non-defined columns are there within the index itself. And so non-clustered is preferable when you have, like I just said, where you have order by, or when you have the leading columns, where you have greater than or less than's. And again, no need for covered indexes. Not really, you don't know how I think that's a really neat feature. Column store indexes came out in SQL Server 2016. And in in-memory tables, it has to include all the columns within the base table. And then as a result, if it's going to be all the columns, you might as well make that your clustered index. You cannot be a filtered index, cannot have large objects like varchar max. And the max row size is 8,060 bytes. And when you do have a column store clustered index, you are going to pay with extra RAM, and I'll show you that in the demo too. So if you look at this chart here, on the far right-hand side is the disk-based index, and yes, you can do index scans, you can do index seeks on equality predicates, you can do index seeks on inequality predicates, you can retrieve rows in the sort order matching the index definition. And then for disk-based index, you can retrieve rows where you're doing, instead of ascending, you're doing descending for one of the columns in your index definition. And so column store index supports the first four. Your range indexes support the first four, but the hash indexes only does the index scan or index seek. Be really careful. This is one of the cons for in-memory tables. If you have a lot of duplicate index key values, the way that it's organized within the C# data structure, it starts running through linked lists and just takes a long time. So Microsoft and several other people recommend that if you have duplicate values, consider adding the primary key column as your second column so that your whole index definition is unique. For example, if you were you want to do a index on dates or update dates, say, you could make it on that, but you might want to consider adding a primary key if your dates are very repetitive. Okay, hardware and table size do matter. When I first gave my first presentation on in-memory tables, I was doing it on a laptop with 8 gigabytes of RAM. It did have a solid-state drive and using VentureWorks 2012. And actually, performance for some of the in-memory tables was poorer than the disk-based table, and the reason being I was getting page swapping. This presentation is with 64 gigabyte RAM on the laptop, terabyte solid state and spinning drives, and 8 logical processors. And I'm using VentureWorks 2017 Big. This isn't a high power server by today's definition, but 15 years ago, this would have been a very high power server. And RAM does make a difference in these benchmarking tests. So if you're working on a development box to do a proof of concept, make sure you do have adequate RAM that approaches what you have in production, because otherwise your results will be different or can be different. All these demos are with SQL Server 2017, but I've noticed very few, I haven't noticed any performance detriments between 2014, 2016, 2017. Also realize that it's difficult from a time point of view to show large data manipulations, but hopefully these demos will at least give you some trends and things to think about. Okay, let's look at demos. Okay, first thing when I get on somebody's computer, I do a select at version, and you can see right here I'm running 2017 and cumulative update 4, and I'm developer version. I already had done the restore just so we have a clean version of VentureWorks 2017 Big. And how did I get the clean version? This is a script I downloaded from SQL Skills and Jonathan, which allows me to come down to the bottom, and you can see sales order header increased from 31,000 rows to 1.3 million rows, and from 100, and then SQL sales order detail increased from 121,000 rows to almost 5 million rows. So let's come back over here. And as part of my script, you can see I did set up and added the file group for memory optimized tables, and also a file for the memory optimized tables. Okay, so let's look at, I want to show just a demo. It's a trivial demo, but it's just something that you just need to see once. Okay, I'm going to create an in-memory table, and down here, I'm going to set the bucket count equal to this number right here. Remember I said we're going to do it on sales order version of sales order detail. Remember I said we have almost 5 million rows. So this is the next higher power above 5 million, the power 2. I have the exact same table, which is in memory 2 right there. You can see where I'm setting it equal to 500,000. So let's run this. And it's complete. And created the 2 tables. And again, here's that same link I had before on bucket count, but the general guidance throughout the literature is 1 to 2 times the number of distinct values in index key. And then I give a little discussion here. And you'll see, I comment my scripts fairly well so you see what's going on. So let's add some data to both these tables. So I use set statistics IO time just to see what's going on. I'm going to turn on include actual query plan. And I have that print star just because I like to have them different, or see the difference in the results. This takes a few seconds to run, but I want to show you that on every query I run, I try to give you the CPU time, the elapsed time, and the query cost. And there's the first one done. And you can see it's going to run about 8 seconds. The numbers will come out slightly different because I can never get them to repeat because other Windows is doing other things in there. But you notice I have, for the first query, I had 3 physical reads. I have time, well, it's a little bit slower today, 9.7 seconds is this point. Previously it'd been 7.4 and 11 seconds, and which is not bad, really, if we're loading 500,000 rows. And then for the other one, I had 9.5 seconds and 10.4. And again, this one, the second one, didn't have the physical reads because I have so much RAM on this computer right here. So let's come down now. And this is a query. You can look at what's in the buckets. And you can see, even though if you remember back up here in this definition for the second table, the in-memory 2 table, I had a bucket count of 5 million. And down here, you can see the second one now has a bucket count of 8.3 or 8.4 million. So even though you specify a number, it's going to round it up to the next factor or 2. If you look further out here, you can see there's a fair amount of empty buckets. The average chain length is 1, which means there's one, for most of the blocks, the average is 1 row per block. But you do see I do have a max chain length of 8, at least in one of the buckets, and that's starting to, if it's usually greater than 5, I try to rethink it, but I'm not going to increase the number of buckets in this particular example because I'm already almost double. And remember, whatever you specify for buckets, there's 8 bytes per bucket, and so 8 bytes times 8.4 million or so. Okay, so I'm going to now, for the rest of the demo, we're going to have look at 3 tables. We're going to look at table 1, which has no indexes except a hash PK, and that's going to be the primary key non-clustered. Table 2 is going to be no indexes. It's going to have a range PK and the primary key non-clustered. Table 3 will be the same as table 1, except I'm going to add in a clustered column store index. So if we look at all these tables, this first one's identical to the one we already looked at just a few seconds ago. And you can see I have the bucket count there of 8.4 million. And down here, you can see there is, it just says for my constraint for a primary key, I just say non-clustered. I don't have hash and I don't word hash. I don't have a bucket count. So we keep going down. Again, the in-memory 3 table there has just identical to the first one, except I have another alter table where I'm adding a cluster column store index. And so if we run these, they don't take very long to run at all. It's complete. Now let's go back and put data back in again. And so what I have here is statistics IO time on. You can see the syntax for running with in-memory tables is very similar to what you're already used to for disk-based tables. You gotta, if you're gonna do a identity insert, you got to turn it on and you got to remember to turn it off. And I'm going to do a select from a disk-based table, and it's going to be about 4.8 million rows. And I'm doing the same thing down here, only now I'm going to go into in-memory 2, which you mean, if you remember, is a range index, and in-memory 3, which has a hash primary key, but also has a column store. So let's run this and just see. And this does take a few seconds to run. I apologize for, but you got to run with big tables or you can't. And if we come down and just as I promised, okay, so we're going to see, and I'll show you the numbers when they come out, but the first one with the hash index primary key ran in about 7 seconds. Then you can see all three have a query cost of roughly the same thing. Look at the range index. It takes longer to do the insert on the range primary key than it did the hash. And if you look at the third one there, it's roughly the same time as the hash. And so Microsoft's very efficient in setting up that column store index, which is the only difference between 1 and 3. And we should be finishing pretty soon. There we go. Okay, so the first one, okay, it took 9 seconds. Again, it's a little bit slower today in 10.4. The reason I put the print stars there is just so I can separate out the data faster. You can see it went the other day, yesterday, it took 16 seconds. It took 20 seconds today and 21 seconds. And then down here, again, 9 and 10. And if I come up here and look at the execution plans, they're all identical. They're doing a clustered index scan out of the big table and doing a table insert, table insert. Notice down here, it says for the third one, the clustered index insert. Okay, if we want to look at what's going on size-wise with these tables, you can see that the memory allocated for the tables is roughly the same, a little bit more for the column store because the column store is an additional index that you need to make space for. Roughly the same amount of used, again, a little bit more for the third one because of the column store index. The allocated, and I don't understand why it allocates more, considerably more than it needs for the range index, but it does. And again, now, but for the column store, you can see it's much more than the hash by itself, and then it's using almost everything that it does there. So there, you are paying for a column store. And again, there's the numbers there. And if we go over, let me switch back just a second to there and come down one. Whoops. And I think graph-wise, you can see that the hash plus the column store is taken up, allocating much more than the range and hash are roughly the same, except you can see it allocated more there. But again, the amount used was roughly the same, and the column store is going to be more. Let's go back to Management Studio again. And just like disk-based tables, in-memory tables like to have their statistics updated. So again, the neat part about the way Microsoft put together in-memory tables is that everything you know about T-SQL, very little's changed. And you can see it takes about 6 seconds for the statistics on the hash index, a little bit over 3 seconds, so it's faster for the range index, and then even faster for the column store. Now, if we go back and look at bucket count again, like I did, this is the same query we did earlier, you're going to see more numbers than you want, like these three here. And I found this about 2 years ago, right after 2016 came out. And it turned out I and a gentleman up in New England and a gentleman over, I think, in Germany, we all found it at the same time. The guy in Germany actually logged it as an error with Microsoft, and it just is an error. But so if you only look at the first two numbers, you can see the bucket counts look really close to what they were before. Again, we have that chain length of 8 for a max, which is not the best performance. Okay, so let's look right now at a select statement where just out of the first one, where we're looking at the sales order ID equal to a specified number. And if you remember what I told you before, it's doing a table scan. Well, why is it doing a table scan? Because that's the first column in the hash index. And if you remember what I said before, hash indexes require, if you're going to use them, you require all the columns to be there for it to use that hash index. So, you know, it's not terribly bad performance-wise. 1.7 seconds CPU, and then about 0.3 seconds, a third of a second for duration. But because it's doing a table scan, you had a query cost of 6.07. Now, if you go back in and add the second column of the hash index, let's run this. And if you look at these numbers here, they look very similar to these three numbers right here. If I run this up here, we look at the execution plan, and it did do the index seek on the primary key. If you look out here, you can see that it is the primary key that it did the index seek on, and now the query cost is 0.0000175. So very fast lookup if you include both columns. But again, not a fast lookup if you only include one column out of the two. Notice the PK is acting like a covered index. You're not having to do key lookup or anything else. It's all right there. What's also interesting, if you come back and look, the parse and compile time is actually longer than the execute time. So think about that not only for in-memory tables, but also for disk-based tables. If you're running a stored procedure with recompile all the time and you're executing it 10 times or 1,000 times every 10 minutes or so, then that might be some issues you want to look at too. Okay, so now let's compare performance between all three tables. We're going to do look at just a plain select. It's all exactly the same query, except I'm looking at different tables. And if we run this, you look at the execution plans, 4%, 93%, 4%. Okay, remember we said that hash indexes are very efficient when you have both columns in there, and that's kind of what we expected. Let's go look at the statistics. And well, today it's running 395 for the first one, 0 and 160 for the second one, and 0 and 94 for the third one. This is numbers I got previously, but you can see, you know, come back up here because it's doing an index seek on the range index. If we look at the query cost, it's larger than the query cost for the hash index. So hash indexes are good if you have exact points you're looking at. So let's look at an update on almost 5 million rows. Oh, stop. No. Oh, I'm sorry. I didn't. And I'm going to have to come back up here and recreate the tables again. Okay, so let's come back down to where we were. Okay, that was the one we just did. This is the one I want to do, but I have to wait till we get our data back. Okay, so here we're doing an update. All we're doing is just changing one column. We're setting unit price and increasing it by 5%. And I'll run this as soon as I can get the data back in the tables. Are there any questions in the meanwhile? Okay, so let's run this now. This takes a few seconds because we're updating 5 million rows roughly.
Yes, there's a few questions.
Okay, let's go ahead while we're waiting.
To reduce duplicate values in adding the PK column, do you include the PK column or add it to the column list of the index?
I add it to the column list of the index.
And then what is the advantage of a column store index over a hash index?
You'll see that in a little bit. I'd like to defer that to the advantage of a column store is performance improvement in select statements, a potential performance improvement.
Right. This is being recorded, and we will be posting the recording along with the slide deck and the I guess the queries, if you're going to send those to Sharon as well, those will be on our site. And at the end, we'll have Mike put his slide back up so you can see where you could download yourself as well from his site.
I hadn't put it up for downloading, but Sharon has the file as well as you do too. Okay, right. So this update, okay, you can see we did put in and roughly 6 seconds for the update on table 1 where the hash index is, and at roughly the same times for the range index. But look what happened on the hash index with the column store. And that's actually pretty reasonable because it had to rebuild that entire column. It had to rebuild all 5 million rows for the column store index for the unit price. So that, and you can see here, execution plan, we have different numbers here. Or no, 38% and 38% and 24%. You can see the numbers right there. So in this case, the column store is not helping you out because it's having to rebuild it on the update. Okay, so let's look at another update, and this one's going to be on a lesser number of rows, and we're going to join it to a disk-based table, production.product. So if we run this runs a little faster. Same indexes again. We haven't changed anything yet. And we come down and look. Okay, so about a second for the hash base index. You can see product is a disk-based table, and so we are doing reads out of it. About a second for the range index, and then a little bit more. So the column store didn't hurt you as much here, but it does add some overhead because it's having to rebuild that on those few columns that were there. Again, there's no logical reads. If you look at the I/O, there's no logical reads on the in-memory tables. The only logical reads are coming off the disk-based table. Okay, if we look up here, it's asking for a index. It's asking for index, and that's the index it's asking. And if I run this, I get an error. Create index is not supported with memory optimized tables. So Microsoft didn't, I hope this is a bug they have that they'll fix eventually, but you can't create it like that. But you can create indexes with the alter table. And so I'm going to run those two. But if you try the third one on the in-memory table, you get an error message that says alter table is not supported with memory optimized tables that have a column store index. So if you want to add an index to a table that has an existing column store index, what you're going to have to do, if you look down at my next statement right down here, you're going to have to drop the column store, add your index, and then create it back again. And actually, it goes faster than you think it might go. Okay, so now I've added a range index or a hash index on product ID, a range index for the second table on product ID, and then I've added a non-clustered index, range index for the second one. So now the first and third tables are not quite the same because the first table has a hash index on product ID, and the second table right here just has a range index. You can just see that non-clustered, there is no hash in there. So now that we are there, let's go back and rerun that same query we just ran earlier. Only now we have the indexes. And this gives some interesting results also. Okay, times, look at the execution plans. We have 32, they changed a little, 32, 34, and 34%. And you can see that it's doing index seeks all along for all tables, both the in-memory tables and also the disk-based tables. And you look at over here. Okay, so you have about 1/10 of a second. You have about a 1/2 second for the range index, and you have about a 1/2 second for the column store. Again, the column store now is actually faster than the range because it was a small number of things. So let's do some cleanup. And again, I can't do the alter table and drop the range index there on the third table unless I delete and then add the column store back in. Okay. This is an interesting coming up. Okay, so we got it back. We don't have any, we're back to our standard tables without any extra indexes. And if we run that, with execution plan, we have 46, 46, and 8%. Somebody just asked, Julie, or said somebody to ask about column store indexes. Well, look down here. Okay, so we were doing a table scan on the first two tables, and on the third table, which had the column store, it's doing a column store scan. And look at the difference. I mean, 46%, 46, 84. If I come over here and look at the cost, I have 6, 6, and 1. So a factor of essentially about 6 improvement in query performance just by using the column store index scan. So I hope that answers the question that was asked. If not, re-ask it again and we'll go back through that. Okay, so column stores do work sometimes they work better for select statements than you would think. And again, the column store index scan right there. Okay, so let's look at specific points in the primary key, similar to what we had earlier, but not exactly. And again, you have all these where you can go through them at your leisure later on. If we look at the execution plans, we have 87%, range index is 0, and the query is 30. But again, look why the range is faster. The range is doing a table scan. I mean, the hash is doing a table scan. The range is doing index seek, and the query 3, it's not doing a table scan, but it's doing a column store index scan. Hence the improvement or so from, well, let's look at it. So your cost there is 0.001, your cost here is 1.05, and your cost there is 6, almost 7. So this shows that it's going to try to take advantage, and the optimizer is fairly good at picking the right indexes to use. And if the range index is available, it's going to use that. If I had a range index up here for this, it would have used it. It used remember, we did put a range index down here on this particular table, and it still used the column store. No, I'm sorry, we didn't do that. We took it back off. All right. Numbers, again, just as we talked about before. And it didn't use the hash index for the first case because we only specified one of the two columns. So let's look at a range case where we're looking at a difference in modified dates. We look at our execution plans. Come on, clean up. Okay, so we have 46, 46, and 7, which is about what I got yesterday. And if we look at times, the first one took about 1.9 seconds. Again, about 1.9 seconds for the third, or the range index, and then columns. So I suspect we come back and over here and look, it's going to be using the column store index again. Again, column store, it peruses it faster in this case than even the range index. But we don't have a index yet on modified date. And notice it didn't ask for one either, which is strange. I don't quite understand why it asked earlier and it didn't ask now. Now, if we go back in and add a hash index for modified date, we know it's not going to be great because it's a range period that we're looking over. But we're going to, and then for the second table, we'll use a non-clustered. And for the third table, we'll use a non-clustered also, rather than a hash index. So let's go back and run these. And it should be finishing up about now. And it did. So now we have those indexes there. And let's look at run that same query over again. And now we look at our execution. And we have 70, 19, and 11. If we look here, it still did a table scan on the first one because we don't have, because it's a hash index, and hash indexes don't work good over range of values. If we look here, we did an index seek, and it did use the modified date there. And it's seeking between 7.1 and 7.31. Down here, it used the column store, even though it had the range index available to use, it still used the column store. So 11 versus 19% versus 70%. If you look at our query cost, 6.8, 1.8, and 1.05. So again, column store here is actually giving better performance than the range index right here. All right, so let's go down to our, and that's essentially what we had before. And I'm not going to run this, but if you try to generate more than 8 indexes, you'll get this error message down here that I have highlighted. And that kind of gives up. Let me clean up, and then we'll go back to PowerPoint. And okay, so what did we learn? One thing I'm frustrated with this presentation in that I haven't been able to give you really good guidelines on when to use what. But hopefully I've given you some ideas of what can happen. And as you'll see in my last conclusion, you got to test, or else you don't know where you're going to end up with. Anyway, hash indexes are most likely best used for your non-clustered primary key. And probably that's all, because anything else, unless it's unique, is not going to give you very good performance. Range indexes as needed, and those are only needed for your really select queries. Although I'm now working on a blog where covered indexes are also not only used for select queries, but also for updates. But that's coming out in the near future. Okay, in my mind, column store as needed. Remember, test all your possible data scenarios. The problem with column store and range is they take up extra memory. If by taking up extra memory, you may not have enough RAM. But remember, okay, and so you have the performance there. Okay, so they may offer considerable performance enhancements when needed. They come with a cost. You need to make sure you have enough RAM. In any case, test. And just as a side note, this is something that's really bugged me, and I keep asking Microsoft, and they keep blowing me off. But anyway, nobody's really addressed the trade-off of your buffer cache for your in-memory tables and indexes. And one thing I haven't addressed in this particular briefing is that in in-memory tables, they're almost one of their best uses is when you have concurrency issues. Okay, all kinds of references there. You can did it. I thought Neil Otter and I, we probably ought to put together a dual presentation. He presents the theory real well, and I hope I give some good examples. Questions, and then for any of y'all that are close to Dallas, Texas, I'll be there May 19th and giving a presentation on climbing the SQL Server Index B tree. So again, I thank you for your attendance, and I'm open now for any questions.
One more question. Is it a best practice to put lookup tables and their indexes in memory and the data tables on disk?
If you have the RAM available, I would do it. The best use of in-memory tables are for staging tables for data, moving it from one server or one database to another. Our session tables and in-memory tables are actually very good for as a replacement for temp tables. So is it a best practice? I would try it and see, but you're going to have it right there available. And if it's a small table, then why not put it in RAM? But I'd try it, experiment and see. Any other questions? Okay, if there's no more questions, then Julie, you want to take it back over? Or?
One more. Have you seen any improvements in performance using column store indexes for lob data?
Okay, if you remember earlier, I said that for lob data, you can't use a column store index. So if you have a table with lob data in it, then that you cannot put a column store index on there. And the one difference between in-memory tables and disk-based tables on column stores, in column store on disk-based tables, you can specify what columns you want to put in the column store format. And in-memory tables, all the columns go into column store, and with lob data, you can't, it just doesn't organize into column store. So I don't know. I think that answers the question.
And that's all. Let me scroll down one more. Let's see again. Whoops, another question. What's the difference between in-memory column store and include index? Column store and is column store is good for OLTP data? Two questions there.
Column store is good when you're using your tables for a fair amount of reads. And again, though, you have to test it to make sure your select queries are addressing the tables that are in column store. If you're just loading data in, you really don't need column store. What was the first question again, Julie?
What's the difference between in-memory of column store and include index?
Okay. Include is for disk-based tables. So include is usually used when you have a covering index on a disk-based table. Remember, you don't have to cover in in-memory tables. So for include is, and if you were at my presentation in Dallas in a couple weeks or 3 weeks, I covered that exactly and showing how include puts the actual data in the index itself down at the leaf level. And if it's the data's at the leaf level, that means there's less rows you can compact per page, and so your index gets bigger. Not that that's necessarily bad, but that's just what it does. On the column store, though, is it actually physically rotates the data from horizontal to vertical and stores it that way, and then it compacts it as best it can. And if it by compact, and then now it can go through faster to find out what if say on that modified date what date you're looking for, and it'll have one value for, say, if you have 10 on the same date, it'll find one value, then point to those 10 values there. They're different. It's a different topic altogether. It's a different function.
And let me check one more time. That looks to be all the questions. Mike, really wanted to thank you for your presentation. Again, this lecture is being recorded and will be posted on the DBA Virtual Chapter website under archives, and we'll also have the other information that Mike sent us. We'll post that on the website as well. Again, thanks again, Mike. This was a great presentation on the in-memory indexes. Thank you, everybody, for attending.
Thank you. Bye.
Bye.